Swayam Prabha. Digital India. Educated India.
So dear students, before we go to the coupled circuit, let us first understand the effect of mutual inductance which is appearing in the circuit. So the mutual inductance the effect was M. As we have seen that the voltage will be appearing V12, which is the voltage induced in 1 due to 2, so this will be I2 by dt, and V voltage induced in coil 1 due to 2 is nothing but M di1 by dt. Okay, so this is the effect of mutual inductance. So this is basically appearing as a voltage dependent source, correct? So voltage in coil 1 is depending upon the current in coil 2. Similarly, voltage in coil 2 depending upon the current in coil 1. So what is happening is, if this is a coil 1 and this is a coil 2, I1, I2, V1, V2. Okay. Now, how will be taking the effect of V12, which is basically a dependent voltage source, right? So this is basically a depending voltage source V12, and this is also a dependent voltage source. But how to decide the polarity? Whether this will be this or this will be taken as this. So this will be defined by the direction of the current. So before we look into the direction in the current, so this will be V12. Similarly for V21 also, we do not know the direction of the current, so that will decide the polarity. This can be this way or this way. Okay, so now to confirm this, or to fix the direction, or to know the direction of the induced voltages, first we have to find some convention which is known as the dot convention, which will tell you the polarity, or this is also known as dot notation. So what is the rule for this? So the rule is, if the coupled network or the coupled circuit, both the currents in the coil 1 and coil 2 either entering into the dot terminal or leaving the dot terminal. So in both the cases, whether the current are leaving or entering, but it is happening same way in both the these coils, then we take the effect of, M will be positive, and the polarity of M will be taken as the same polarity of the self. If the self inductance is positive, then this M will be also be positive. Otherwise, the second condition is, so this is rule 1. The rule 2 says, if the current in one coil leaves the dot terminal, and another coil, the current enters into the dot terminal. The effect of M will be negative. It means that the polarity of the M will be taken as the polarity opposite to the self-induced voltages, or the self voltage due to the self-inductance. Okay. So in these rules, now what we'll do, we'll look into the cases, possible cases. Suppose there are two windings. Okay, so if there are two windings, which is nothing but winding 1 and winding 2, or the coil 1 and coil 2, and this is suppose a dot convention. The voltage is applied here V1, or basically the current direction we have to see, and the mutual is M between these two windings. Okay, and another case is this. So there are total 4 cases possible, so I am drawing all the 4 cases, the current 1, current 2, mutual inductance is M. So this is case 1, this is case B, and this is I2, this is I1, this is I2, this is I1, this is I2, this is a case C, and this is case D. So in these 4 possible cases, let us give some kind of dot notation. So let us give these dots here, and now assume this current as I1 and this as a I2, and one dot is suppose here, one is here. These are the 4 possible cases. So in this case, okay, so in A, the current is entering at the both terminal. So in A, and what is happening in case B, the current is leaving. So if the current is coming here, so it is leaving the dot terminal. Similarly, I2 is also leaving the dot terminal. So in A and B, M is taken as positive. Positive means same as L or self. Similarly, in C and D, if you look carefully, the I1 is entering into dot and I2 is leaving the dot. So M is negative. Look at here, I1 is leaving and I2 is entering. Again, M is positive. Sorry, the negative. This is opposite, right? So M is negative in both the cases C and D. So these are the 4 possible cases where the effect of M is known. So now we are in the position to decide the polarity of the induced voltages due to the mutual effect. Now what are the circuit equations? What do you mean by circuit equation? So let us first draw one case, like I'll demonstrate here for 2 cases. So let us one case is here where the voltage applied here is V1. This is the polarity. The current is going this way. Similarly, this is V2. The current is going this way. And the polarity here, suppose this is the dot notation. Okay, and another case will take the opposite dot notation. So I'll just copy this. Okay, so here in this case what I'll do, I'll just opposite the dot notation. Okay, so here if you write the KCL and KVL equations, so first write the KVL equation for KVL equation for coil 1, then it will be V1 is equal to L di1 by dt, and what is happening to the mutual will be same as M di2 by dt. So from here, if you try to draw the equivalent circuit, which will be nothing but one drop in the inductance, which is L, then you have a dependent voltage source, and the polarity is drop. In the direction of current, it is positive, so it is drop M di2 by dt. This is V1, and this is I1. So this is the equivalent circuit of coil 1. Similarly, KVL for coil 2, here in this case if you write, it will be V2 L di, or we can have is L1, right? The coil 1 is L1, so this is L1. So this is L2 di2 by dt plus M di1 by dt. So similarly, from here, if you draw the equivalent circuit, some self-inductance L2 of the coil 2, then a dependent voltage source, and in the direction of current we have to take this positive, means it is a drop again. So whatever the polarity of L, here M, so this will be M di1 by dt. The current I2 is here, and this is V2. So this is the equivalent circuit. Equivalent circuit means the equation which we have understood as a voltage drop, right? So this is how we have drawn. Similarly, if you see in the second case, so here if we apply KVL for coil 1, this is coil 1 and this is coil 2. So here if you see, V1 can be written as L1 di1 by dt M di2 by dt. What's the polarity of M now? See, I1 is entering into the dot, so this is I1, sorry for that. So I1 is entering into the dot and I2 is leaving the dot, so this will be negative. Similarly, V2 will be L2 di2 by dt minus M of di1 by dt. So from here, if you try to draw the circuit from dependent voltage, so this is V1, I1, L1, this is M di2 by dt, and it is what? It is negative, right? So it is negative, is positive. Similarly, the second winding or the coil 2 will be represented by this way, where it is L2, this is the voltage V2, the current which is flowing is I2, and the polarity of M di1 by dt will be negative. It means that it is rise, drop, it should rise, correct? So this is how you are going to decide the polarity of the voltage based upon the dot convention. So till now what we have seen, we have understood the effect of mutual coupling, and then one part of the circuit which is being producing the energy, or which is energized, and the energy is transferring to the secondary network or the other part of the network. Now if these equations have to be written in the frequency domain, right? In frequency domain, highlight one of the case. So V1, the case 1, if this is the case 1, V1 in frequency domain will be j omega L1 I1 plus j omega M I2, and V2 will be j omega L2 I2 plus j omega M I1, and in case 2 the frequency domain V1 will be nothing but j omega L1 I1 minus j omega M I2, and V2 will be j omega L2 I2 minus j omega M I1. So these are the frequency domain representation of the same voltages, or the KVL equations in the case 1 and case 2 respectively. So let us now consider one example where we just write the equations and see whether we have understood the concept clearly or not. Okay, so what we will do, let us consider one example. So go to this page and draw one circuit. So we have some resistance, and then we have a coil. Similarly, here we have some resistance, and this is a coil, and these two coil is having a dot notation of this type, and there is a mutual which is linking these two. So this is R1, this is L1, this is L2, and this is R2. Suppose current is this I1 with a voltage polarity V1. Here is this V2, and the current is entering into I2. So if you see, the current direction is this way, and here the current direction is this way. Correct? So now what we'll do, we write the KVL equation. So what is the KVL equation for coil 1 and coil 2? So for coil 1, so when we write the KVL equation, we'll start from this point. We'll write the total voltage V1 minus R1 I1 minus L di1 by dt. अब look at the polarity. The polarity of M will be same as L if the dot convention having the current inward or outward. So in both the cases, coil 1 and coil 2 are mutually coupled, and the dot notation is such that the currents are entering into it. So this will be positive, means the polarity will be same as the self. So this is basically minus M1, or basically M is same. So we'll have only M di1 by di2 by dt is equal to 0. So here actually we have written all the right term side. So V1 is nothing but R1 I1 plus L1 di1 by dt plus M di2 by dt. So this is the for 1. Similarly for 2, if you write, this will be like R2 I2 plus L2 di2 by dt plus M di1 by dt. So this is the KVL for coil 2. Okay, so this is how you are going to solve these equations. So this is an example where we have taken the resistance also in series with the circuit. So now whatever the circuit is connected here or here other side, we can clearly indicate and find out the values as we did in the case of normal circuit. So only one dependent voltage source will be present in each part of the circuit, which is mutually coupled based upon the mutual inductance. Dear students, so far we have studied the magnetics basics, and now let us consider some of the example. So we'll consider one example for finding the electrical equivalent circuit of a magnetic circuit. So since we have already understood the mathematics which is involving for the calculation of reluctance and other mathematical formulas. So now consider one circuit which is a magnetic circuit having a magnetic core. Okay, and suppose this is the core of the magnetic circuit. Okay, so we assume that the mu of the core is infinity, and here is your excitation winding which is connected having a current I. The area is this A1 and this is area A2. This is the cross section area. The gap you can assume as G1, and here this gap can be G2, the gap length, and it is having n number of turns. Okay, so the magnetic circuit which is given this, you can find there are n turn winding. So we have to find the inductance of the winding and the flux density. So in this circuit we have to find inductance of the winding and then magnetic flux density. In gap G1. Okay, so what we'll do, we'll neglect the effect of fringing and then apply the mathematics. So we know that the MMF is nothing but Ni, which is nothing but 5 times of total reluctance. Okay, so this is a flux which is flowing in this core, and you see here at this junction the flux will go through the air gap G1 and G2. So here also it will go. Now clearly you see one resistance will be appearing here, and if you assume mu infinity, that reluctance will go to 0. Okay, because the reluctance is given us the gap length which was Lg by mu A of cross section. Okay, so whatever. So if mu goes to infinity, then the reluctance is, this is the reluctance which will tend to 0. So cannot be infinity, it always tends to infinity, correct? So this is a condition. So the resistance in this part or the reluctance in this part will be 0. So the electrical equivalent, if you want to compute, you have to have the one reluctance which will be appearing here in this portion and one here, because these are the gap length. Rest in the core you'll never have any reluctance because the mu is taken as infinity. Now what is R1? So R1, suppose for example for gap G1 we have reluctance R1, which is nothing but gap length is G1 by mu times of A1. So mu is here gap, air gap, so free space mu naught, right? Similarly for gap G2, the reluctance R2 is nothing but gap length G2 by mu naught of area is cross section A2. Okay, So what will be the total reluctance? So if you see clearly the electrical equivalent circuit, the effective reluctance we have to find. So this is a kind of electrical equivalent circuit. This is new Ni, this is R1 and this is R2. So what is the reluctance which is being be seen? So flux phi is here, so here it can be phi 1 and here it can be phi 2. Okay, so the total reluctance is nothing but the R total, right? The parallel combination of R1 and R2, which will be reluctance R1 R2 by R1 plus R2, correct? So from this R total, next step will be calculating the inductance, right? We have to calculate the inductance. So inductance is nothing but N square by reluctance, right? This is total reluctance. So now you can put N square R1 plus R2 times by R1 and R2. This is reluctances, okay? So now you can put R1 R2 from here. We have both the values, and then you can calculate the phi also. How can you calculate the phi? Phi is nothing but MMF Ni by total reluctance R total. This is RT. Okay, so this is R total. So from here you can calculate the phi. Similarly, B1 is nothing but the phi 1 by A1. Okay, and phi 1 is nothing but total reluctance by R1, and phi 2 is nothing but total reluctance by R2, because here if you see across these two resistances, the voltage like it is maintained same. So the flux which is going is this mmf by this reluctance. Similarly, the flux which is flowing through R2 is this nothing but same mmf across this reluctance. So from where we get the equivalent circuit here. And if you want to calculate B2, that will be nothing but phi 2 by A2, and the phi 2 is calculated from here. So this is what we are supposed to do in any numerical, or the similar expression will come. Okay, so you have a different kind of circuits, then you can solve it using the same. You have to first understand the concept of reluctance, which is equivalent to the resistance in the circuit, electrical circuit, which we are familiar with, and then apply these kind of numerical calculations. So now if we just look into the another circuits, for example, you may have this, you can solve such circuit you can find in the okay, so here you apply the current I with number of turns n, and then you have a air gap. So I'll draw the gap with red color. So from here you have a gap, and one gap you have here. Okay, so this is nothing but the air gap. Okay, now in such cases also you can find the electrical equivalent circuit, how it will be, and then what is the flux which is flowing, then what is the flux which is getting divided in phi 1 here and phi 2 here. Okay, so phi 1 here and phi 2 here, the total flux phi which is here, and the reluctance. Such calculation you can always make, and you can solve the questions from the references which are being shared. So now let us understand the effect of mutual inductance in a circuit. So we will now consider some of the circuit So again, some example on mutual mutual inductance, right? So first we'll consider some easy, so that it will be easy for us to understand the concepts, right? So suppose there are two windings, okay, and this is the dot notation. The current which is flowing in is I1, number of turns is N1, then the inductance correspond to this is L1, and the voltage which is being applied is V1. Similarly, the output voltage is applied, which is V2, and current which is entering is I2, the inductance corresponding to N2, and the number of turns is N2. And M is the mutual inductance. If you are given K, like the coupling coefficient, right? If K is given, which is nothing but coupling coefficient, so K is nothing but the value which will be is from 0 to 1, okay. And if you want to calculate the mutual inductance from given K, is nothing but K times of root L1 L2. Suppose here in this case K is 0.5, then L1 into L2 square root of that into 0.5 will be the M. But if M is given directly, you can use it. So it depends what is the parameter which is given to you. If there is no K, then M will be given. If there is no M, there will be K, some coupling coefficient will be given. So there will be two voltages which will be getting appeared from this side. One is the voltage source V1, the voltage drop across the L1, and the voltage which will be appearing through the mutual inductance of the current I2. So if we write the KVL equation, so V1 will be nothing but L di1 by dt, this is the mutual component, and M di2 by dt, this is the current I2 and the mutual inductance M. The polarity of this voltage will depend upon the dot notation. So here if you see in the dot, the current is entering into the coil, and here if you see another coil, current is leaving. So this is the negative. So when L is positive, it will be negative of that. Similarly, if you see V2, it will be L2 di2 by dt, which is a self inductance, self component, and then mutual component will be, okay, we'll see minus of plus, negative, then M di1 by dt. So here the current is I1. So here the voltage which will be appearing in the coil 2 will be coming from the current I1, which will be induced through the mutual inductance M. So this is how the equation will be written for mutually coupled coils. Once it is done, you can solve the circuit and then evaluate the parameters, whatever the questions are being asked. So now the equivalent inductive reactance, if you want to compute, so let us consider one more example. So suppose there is a core, okay, and there are three windings, okay. And you have a dot notation which is given as one dot is here, and another dot for this winding is here, and another dot is suppose here, and the current which is flowing is okay. Now in this case, when the current is flowing here, if you see the current is moving in this direction, okay, Now you have to draw the equivalent inductive reactance. So if we assume this is given as, the self component is given as J2, the self of this is J4, and this is J5. The mutual component between 1 and 2 is J1, and 2 and 3 is J2, and 3 and 1 is J4. Okay, so this is the so what we have to find? We have to find the equivalent inductive reactance. Now let us draw the easy circuit, which will be easy for us. One inductor, two inductor, three. So it is J2, it is J4, it is J5. So consider this as 5. And the mutual between 1 and 2 is J1. Between 2 and 3 it is J2, and between 1 and 3 is J4, and the dot notation is here, here, and here. Okay, so in this circuit we have to first understand the, like L1 will communicate to L2 and L3, L2 will communicate to L1 and L3, and L3 will communicate to L1 and L2 through the mutual inductance. So there will be 6 terms: L1 L2, L1 L3, L2 L1, L2 L3, L3 L1, and L3 L2. Okay, this is very important to understand. So if when we're going to write the ZL, which is the total inductive reactance, it will be L1 plus L2 plus L3, then mutual term will come. Okay, mutual for L1, mutual for L2 plus mutual for L3, and we will see the direction, I mean the direction of current which is entering to a dotted position. So sign we'll see later. So now what will happen? So the L1 which is here is J2 plus L2 which is J4 plus L3 J5. Now L1 will be having with L2. So L1 L2 mutual inductance is M12, which is J1. Now J1. Look at the polarity. So in 1 it is entering the dotted position, here it is leaving the dotted position. So it is minus J1. Now L1 with L3. So L1 will communicate to L3 using J4, and the polarity is same, J4, because both in L1 and L3 the current is entering the dotted position. Now L2 will communicate to 1 and 2. So now 1 and 2, M12 will be J1, which will be minus okay, minus J1. Then we have this J2, which will be again minus. Okay, then we have this minus J2 again, then we have this plus J4. Okay, so now if you'll see 4, 2, 6, 5, 11, 10, 14, 13, and it will come out to be 13. So J13 is the total inductive reactance of the circuit. This example is very essential to understand. When there are 3 coils, there will be 6 terms. So each coil L1 will be having a mutual inductance with M12 and M23 and L13. So remember always this Okay, now for example, if we write one circuit, I'll draw one small circuit and just try to understand that. Okay, so suppose this way. L1, L2, L3, M13, M12, M23. So in this case also, suppose some dotted positions are given. Suppose some random positions. Okay. So here also you have to see that L1 will be having a voltage drop. Then two terms will appear here. Similarly, this term and two term will appear here. And two term will appear here. So this is L1, which is L di1 by d2. This is L2, and this is L3. This is L3, and this is L2. So one will be M12 di2 by dt. Then M13 di3 by dt. The polarity you can see based upon the dot notation. Similarly, these are two terms. So here it will be M di1 by dt and M di2 by I2 by dt. Then here it will be M12 di by dt, M21 basically. So and here it will be M23 di by dt. The polarity you can see based upon the dots. So suppose one dot is here, one is here, one is here, I1, I3, I2. So now if we want to place the polarity, so we have to pay attention the current which is entering at the dot notation. So if it is entering in the dot notation, here also it is entering into the dot notation, here it is leaving. So I2 will be negative and this will be positive. You can write the equation and see. Similarly, this term if you see, the current I1 is entering the dot position, here also it is entering, so this is positive. This current is entering and this current is leaving, so here it is negative. Here if you see the current which is entering in I1, sorry, this is I3 then. Okay, let us write these terms again clearly. So this will be M into 1 di1 by dt plus M23 di3 by dt. So 2 1 means the current in the 1 is entering the dot position, it is leaving, so that will be negative. The current which is entering in the 2 and 3 if you see, it will be again negative. Correct. So this is how the polarity of the M will be decided. So there also you see that three different terms are appearing. One self, two mutual, one self, two mutual. So that depends how your configuration is connected.